Kocher published a paper, and there was a lot of discussion in the cypherpunks mailing list. And I want to bring you another fascinating discussion from the cypherpunks mailing list. And this is written. William Simpson was one of the co-authors of the IPsec network security suite, which was using RSA, and Photolis is one of the key distribution mechanisms there. And he was replying, saying, listen, okay, so Kocher found this timing attack. I'm not worried about it because we're going to fix it. How are we going to fix it? We're going to fix it by dithering the return time of the identification method. A few extra milliseconds on top of a second won't be a problem. So what is the William Simpson tradition? They have a function called identification message, which takes a long time to calculate. And when they finish calculating, they're not going to transmit it immediately. They're going to wait until exactly 0000 milliseconds. So they're not going to be using randomness because randomness is very expensive in computers. They're going just to use what's called block. It's called floor. Something with a floor, rounded floor. They're going to round it to a floor. So effectively, because the start time is random, they're effectively adding a random delay without using up the expensive randomness which the computer has. So he says, you know what? So don't worry. It's an extra millisecond on top of a second. It's such a slow computer, such a slow system. Adding a few milliseconds won't be a problem, and not completely solve Kocher's attack. And to this answers Ron Rivest. Ron Rivest, the R in RSA, very, very clever researcher, and he answers as follows. This helps to reduce the leakage of the key information, but does not eliminate it. The best thing to do is ensure that public key computation time is constant, independent of the message being encrypted. So you see, we talked about two kinds of countermeasures. There are mitigation countermeasures, and you know there's a nice word in Hebrew now for mitigation because of the epidemic. It was written down, I forgot it. A nice word. Mitigation is like social distancing and stuff like that. So mitigation is adding this dithering, but Rivest is saying you have to do prevention. You need to rewrite your code. And now Rivest continues, and he says something very insightful. As a side note, I suspect this sort of attack is probably extremely difficult to mount in the internet environment due to timing variabilities. However, it's wise to be careful. So in 1995, Rivest said it's wise to be careful. In 2003, Dan Bonnet wrote a fantastic paper called Remote Timing Attacks Are Practical, a textbook paper, where what did he do? He mounted this sort of attack in an internet environment. Fascinating paper, and you will be happy to learn that remote timing attacks are still practical. There always works on all sorts of crazy timing attacks. So Ron Rivest was right about being careful. So we saw here two possible countermeasures. One of them is hiding, and one of them is masking. And I want to tell you about a really, really nice countermeasure called RSA Blinding, a very, very commonly used. What's nice about this is it's kind of a magical prevention countermeasure, in the sense that usually prevention countermeasures get you to the worst case. Because you always have to plan for the worst. So if you have a computation which is usually fast and sometimes slow, you have to make it slow. If it's usually non-battery intensive and once in a while it's battery intensive, you have to eat the battery. But RSA Blinding uses a very, very nice algebraic trick to actually reduce all of the cases to the random case, the average case. And how does this work? Who here has seen RSA Blinding before? Did anybody see RSA Blinding in the past? No, so I'm happy to show it to you. It's a fascinating idea. So the idea is I want to calculate m to the power of s modulo n, and I don't want to leak s. Because as Kochel showed, the time that this takes is a function of s, and then I can do all sorts of very interesting attacks. So how does this attack work? You wake up in the morning. You don't get, you haven't been, you didn't get their query yet. You're just sitting there and waiting for something to happen. So you're going to choose a random R. And as I said, randomness is expensive. It's not very easy to choose a random R, but you can be consoled by the fact that you can do this even an hour before the data starts arriving. So if you do it once in a while, you can get a random R. And now, again, before you get the message to sign bichlal, you calculate R to the power of V modulo N, and the inverse of R modulo N. So so V is the verification key, signing and verification. So V is the public key. So calculating R to the power of V doesn't use the secret key, and also inverting doesn't use the secret key. But anyway, you don't have to do it while you're being measured. You can do it again. You can do it in the background a long time, right? And now it's showtime. Now you get a message M, and you need to sign it. And now I'll show you how you blind it. First of all, you calculate X, which is equal to R to the power of V times M modulo N. Where did R to the power of V come from? We calculated it earlier. Is there any secret information in the calculation of X? Are there any secret inputs here? The answer, of course, is no. There are no secret inputs here because M was given to you by the adversary. It's known to the adversary. And R is completely random, and V is completely random. V is public. So I take a random number and I raise it to a public value, and no secret information was used here. The value of R should not leak. We assume that it was generated when the attacker wasn't there. Okay, kind of cheeky. So let's continue. Now I have X, and now instead of signing M, I'm going to sign the blinded number X. So Y is X to the power of S, which is R to the power of V times M to the power of S. I open the parenthesis. I get R to the power of V times S times M to the power of S. V times S, we chose V and S. These are the public and private keys. We chose them such that their multiple is 1 modulo phi of n. This is the entire idea of RSA. So this falls out, and all I get is R times M to the power of S. So I get the signed message, and it is blinded. Now, the value of X is unknown to the adversary. And this is why this computation does not help the adversary who is using a timing attack recover any information about S. We're just raising a random. If you recall, the timing attack depended on being able to dictate what is going into the modular exponentiation. But here, this value X is completely random. Completely random. It could be any element of the multiplicative group. So now we have Y, and we take R minus 1, which we calculated earlier. We multiply Y by R minus 1, and then the R and the R minus 1 cancel out, and get M to the S power of M. And again, this calculation does not involve any secret value. So again, it's safe. And the bottom line is we were able to sign the message in average time without exposing ourselves to timing attack. So blinding is really, really nice. It's a really nice idea. Very useful. Actually, many crypto implementations are using it. The disadvantage is that randomness is expensive. If you're trying to do a streaming algorithm or something like that, you will, yes, it's like a feeder in IV, it's like salt. Yeah, the second computation does use S, but the attacker doesn't know what X is, so we can't mount the offensive offensive statistics attack I just showed you, because he doesn't know what reductions are relevant, because X could be any element in the multiplicative group. So it's like I'm adding a seed and then removing the seed, or adding a soft, adding a V. So it's very nice, very useful. There are ways of attacking it using things which are not timing attacks, for example, cache attacks or power analysis attacks. But this is a good idea. Blinding is a good idea. If you have enough randomness, if you're not doing, I don't know, a network encryption device which is using tons of streaming data, usually you'll find yourself doing blind. And now I want to show you a countermeasure which is actually looks really good, but it can be broken. And this is called square and always multiply. And I think I just explained the countermeasure. So if this is binary exponentiation, if I'm going to do square, this is square and sometimes multiply. If I know when r to the power of v is being calculated, if I know r, then I can break the system. Yeah, if I know r, I can measure how long it takes to do r to the power of v. Recall that I didn't look at the output, the sign. I don't have to see r to the power of v. I just have to see how long it takes to calculate. So if I break the random number generator and I have the exact knowledge of what is the value of r, and how long it takes to calculate r to the power of v, which is interesting. How can I find it? Maybe using a cache attack, because it's not used as an output. Then that's correct. R is not raised to the power of s. R is raised to the power of v. But if I know r, I can kind of do. If I know r, then I know x, because I know m. And then if I know x, I can do the previous. But usually you don't know. So square and this is square and sometimes multiply, and we said this is problematic for various reasons, because we can simulate and measure the time. So the trivial idea is square and always multiply is I showed you something very, very similar 2 weeks ago. If d sub I is equal to 1, then I multiply, and if d sub I is equal to 0, I multiply and throw away. And now I will always have the same amount of modular reductions, so my simulations will not be able to tell anything apart. Of course, I will be paying in runtime, but it's not a very big increase in money. It will take a little longer, not much longer. And now there are actually 3 ways of breaking this. Okay, right. So three reasons why this will fail. So reason number 1 is compiler optimization. Indeed, as you said, I'm using what's called a prophylactic write. This is the tempting prophylactic write. The first enemy is the compiler. The compiler will see that nobody is using T, and as a result, it will not execute this code at all, not compile it at all, and in fact, this will be turned into machine code as square and sometimes multiply. So the first enemy is the compiler. The second enemy is the processor. As I said, Spectre. We're not actually using Spectre. We're using regular speculative execution. And speculative execution means is the CPU is always trying to keep its pipeline busy, and is always trying to keep running ahead and executing functions, and it's saying, you know what, I'll execute something speculatively. If I don't need it, I'll throw it away, but I'll execute it. And the thing is that calculating s is equal to s times m, you can't execute it too much speculatively ahead, because each one of these iterations depends on the previous iteration. On the other hand, t is equal to s times m. You can always calculate it because nobody is actually looking for t. So I'm not going to do it 9 minutes before the end of the class, but if you look at it, you'll see that the CPU is going to execute t is equal to s times m very quickly and it's going to discard it for a very, very fast, without even, it's going to take much less time than the regular multiply. Because again, nobody depends on T, so you'll have to fix that. And now the third thing, which is a little more advanced, it's called the operand sharing. In operand sharing, to do that, you need power analysis. And the insight here is that when you do S is equal to S times M, and then S is equal to S times S, you are writing to the variable S and reading from the variable S. So there is one variable being activated. If you're doing T is equal to S times M, and then S is equal to S times S, you're actually using two registers. You're reading from S and writing to T. And now the power signature of these two operations looks different, because you're reading and writing different values in one case, and reading and writing the same value in another case. And there are papers about attacking this. Now, RiskCure is a company that does security certification for a device. So you're building a chip, you want to see if it's secure. You give the chip to RiskCure, and they sit down and say, yes, it's secure, no, it's not secure. So they are really good at these kinds of attacks. Of course, not as good as iStare, but they're doing the best. Yeah. So